Alright, so we know how to find the torque now, but who cares? What good is torque? What good is it going to do for us? Well, here's what it can do. We know from Newton's second law that the acceleration is proportional to the force. What we would like to have is some sort of rotational analog of this formula, something that would tell us, alright, we'll get a certain amount of angular acceleration for a certain amount of torque. And you could probably guess that this angular acceleration is going to have probably something with torque on top, because torque is going to cause something to angularly accelerate. And then on the bottom, maybe it's mass, maybe it isn't. That's what we need here. If we had this formula, this rotational analog of Newton's second law, then by knowing the torque, we could figure out what the angular acceleration is. Just like up here, by knowing force, we could tell what the regular acceleration is. So that's what I want to do in this video. I want to derive this rotational analog of Newton's second law for an object that's rotating in a circle, like this cue ball, and not just rotating in a circle, something that's angularly accelerating, so it'd be speeding up in its rotation or it'd be slowing down in its rotation. So let's do this. Let's derive this formula so that if we know the torque, we could determine the angular acceleration just like we determine regular acceleration by knowing the force and Newton's second law. So how do we do this? In order to have an angular acceleration, we're going to need a force that's tangential to the circle. So in order to angularly accelerate something, you need a force that's tangential, because this force is going to cause a torque. So let's say this is the force causing the torque. We know how to find it now. Remember, torque is R times F times sine theta, but let's make it simple. Let's say the angle's 90, so that sine theta will end up being 1, because sine of 90 is 1. And let's make it simple too in this way. Let's say this force is the net force. Let's say there's only one force on this object, and it's this force here. Well, we know that the net force has to be equal to the mass of the object times the acceleration of the object. And you're probably like, big whoop, we already knew this. What's new here? Well, remember, we want to relate torque to the angular acceleration. So let's write down the torque formula. How do you find the torque from a force? Remember that the torque from a force is going to be equal to the force exerting that torque times r, the distance from the axis to the point where the force is applied. Now in this case, that's the entire radius, because we applied this force all the way at the edge. If this force was applied inward somewhere, it would be only that distance from the axis to the point where the force is, but we applied it at the very edge, so this would be F times the entire radius. And then there's also a sine of the angle between F and R, but the angle between F and R is 90 degrees here, and the sine of 90 degrees is just 1, so we can get rid of that. So this is simple. The torque exerted by this force F is going to be F times R. What do we do with this? Well, look down here. We've already got an F down here. If you're creative, you might be like, well, let's just multiply both sides by R down here. That way, we'll get torque into this formula. In other words, if I multiply the left side by R, I'll get R times F. And now that's going to equal R times the right-hand side. It's going to be R times M times the acceleration. And this was good. Look at, now we have R times F. That's just the torque. Torque is R times F, or F times R. So I've got torque equals R times M times the acceleration. But that's no good. Remember, over here, we want a formula that relates torque to angular acceleration, not a formula that relates torque to regular acceleration. So what could I replace regular acceleration with in order to get angular acceleration? Maybe you remember when we talked about angular motion variables, the tangential acceleration is always going to equal the distance from the axis to that object that's got the tangential acceleration multiplied by the angular acceleration, alpha. So this is the relationship between alpha and the tangential acceleration. Is this tangential acceleration? It is, because this was the tangential force. So since we took the tangential force, that's going to be proportional to the tangential acceleration. These are both tangential here, and these forces are all tangential. That means I can rewrite the tangential acceleration as r times alpha. And that's what I'm going to do. I'm going to rewrite this side as r times alpha, because r alpha is the tangential acceleration. So this whole term right here was just tangential acceleration. And now look what we got. We've got torque is going to be equal to r times m times r times alpha. I can combine the two r's and just write this as m times r squared times alpha, the angular acceleration. And now we're close. If I wanted a form of Newton's second law, I could leave it like this, or I can put it in this form over here and just solve for alpha and get the alpha, the angular acceleration of this mass is going to equal the torque exerted on that mass divided by this weird term, this m, the mass, times r squared. And this is what we were looking for. This is what we're looking for over here. I'm going to write it in this box. The rotational analog of Newton's second law for rotation is this torque divided by this term here, this mr squared. What is that? Well, it's serving the same role that mass did for regular acceleration and the regular Newton's second law. And remember, this mass was proportional to the inertia of an object. It told you how hard it was to get that object accelerating, how sluggish an object is, how resistive it is to being accelerated. That's what this term down here is going to be. People usually call this the moment of inertia, but that's got to be the most complicated name for any physics idea I've ever heard of. I don't even know what this means, moment of inertia. That just sounds strange. It's represented with the letter I, and it's serving the same role. It's in this denominator, just like mass is, and it's serving the same role. It's serving as the rotational inertia of the system in question. So in other words, something with a big rotational inertia is going to be sluggish to angular acceleration, just like something with a big regular inertia is sluggish to regular acceleration. So if this ball, and we can see what it depends on, look at, for a ball on the end of the string, the moment of inertia for a ball on the end of the string was just mr squared. This was the denominator. This was the term serving as the rotational inertia for this mass on a string. And what that means is if you had a bigger mass, or if the radius were bigger, this object would be harder to angularly accelerate. So it'd be difficult to get this thing going and start speeding it up. But on the other hand, if the mass were small or the radius were small, it'd be much easier to angularly accelerate. You could whip it around like crazy, but if the mass were very big or the radius were big, this moment of inertia term would get much bigger. This is the moment of inertia for a mass on the end of a string, and that's what the I is here. So you can think about it as the rotational inertia. That's a much better name for it. People are coming around and realizing that you should just call it this because that's what it really is. This moment of inertia is kind of a historical term that's stuck around. It's not a very good one. Rotational inertia is much more descriptive of what this I really is. And we should note the units of this moment of inertia, since it's mass times radius squared, the units are going to be kilogram meters squared. These are the units of moment of inertia, and this is the formula if you just have a point mass, and by that I just mean a mass where all of the mass is traveling at the same radius in a circle. It doesn't have to be tied to a string. This could be the moon going around the earth, but as long as all of the mass is at the same radius and traveling around in a circle, or at least mostly at the same radius, let's assume this little radius of the sphere is really small compared to this radius of the string. If that's the case, where basically all the mass is traveling around in a circle at the same radius, this would be the formula to find the moment of inertia. So how does this ever get harder? What do you have to look out for? Well, we only considered one force. You could imagine maybe there's many forces on this object. Maybe there's some other force this way. Well, in that case, you just have the net force here to make sure it's m times a, and you just have to make sure you use the net torque up here. So this formula will still work. If you have multiple torques on this object or this system, you just have to use the net torque up here. You add up all of the torques, where torques trying to rotate it one way would be positive, and torque trying to rotate it the other direction would be negative. So you'd have to make sure signs are correct up here. And what about rotational inertia? What if your object isn't as simple as a single mass? What do you do then? Let's look at that. Let's take this formula here. I'm going to copy that. Let's get rid of all of this. And let's say you had this crazy problem. You had 3 masses now, and one force on this mass 2 was 20 newtons downward, and one force was upward, 50 newtons on this mass 1, and they're all separated by 3 meters and can rotate. We're stepping it up. This is complicated. Can rotate in a circle, but we can do it. We can do it with the formula we just derived. So let's use that. This is going to be useful. Let's say the question is, what's the angular acceleration for these masses and this particular setup of forces? We're going to use this formula for Newton's second law. In angular form, we'll say that the angular acceleration, if that's what we want, is going to equal the net torque. How do we find the net torque? Now there's 2 forces. Well, it's not that bad. You just find the torque from each one individually and you add them up, just like you would do with any net vector. Find each individually and add them up. But it's not going to be 50 minus 20. These are torques. We've got to plug torque in up here, not force. This is going to be a torque. And until you multiply that force by an R, it's just a force. So don't try to just stick this 50 up in here. It needs to get multiplied by an R. What R? Be careful. You might think 3 meters. But no, the R is always from the axis of rotation, which is the center, all the way to where the force is applied. So the torque from this 50 is going to be 9 meters times the 50 newtons. Now we've got a torque. It's not a torque until you multiply that force by an R. So that was the torque from the 50 newtons. How about the torque from the 20 newtons? You might be like, all right, I got it now. It's going to be 20 newtons, but I can't just put 20, right? We got to multiply by an R. It's got to be 20 newtons times, and it's not 3, it's always distance from the axis, so it's from the center all the way to where this 20 newtons was applied, and that's going to be 6 meters. And sometimes when people get here, they're just so happy. They remember the R, they just do plus, and without thinking about it, but they're going to get it wrong. You can't do that. Look at this 50 newtons was trying to rotate this system counterclockwise, right? The 50 newtons trying to rotate it this way. The 20 newton is trying to rotate it that way. They're opposing each other. These are opposite signs of torque. So I've got to make sure I represent that up here. I'm going to represent this 20 newton torque as a negative torque. And that's the convention we usually pick. Counterclockwise is usually positive and clockwise is usually negative. But no matter what convention you pick, they've got to have different signs in here, so be careful there. So that's our net torque up here. How do we find the rotational inertia, or the moment of inertia? Well, we know from the previous example that the moment of inertia of a point mass, that is a mass going in a circle, where all of the mass is going at that particular radius, is just mr squared. But now we've got 3 masses, so you might think this is hard, but it's not that hard. All we have to do is say that the total moment of inertia is going to be the sum of all the individual moments of inertia. So if you just add up all the individual moments of inertia, in other words, this is just going to be the moment of inertia of mass 1. If that's 1 kilogram, that's going to be 1 kilogram times r squared. That's what this means. You take all the masses, m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared. You'd keep going if you had more. You just add them all up, and that would give you the total moment of inertia for a system of masses. So if we do them one at a time, this 1 kilogram times the r for that 1 would be 9 meters, because that's distance from the axis to the mass. That'd be 9 meters squared, plus, all right, mass 2. If that's 2 kilograms, then that's going to be times 6 squared. And now we keep going. We take this 3 kilogram mass and we also add its contribution to the moment of inertia, or the rotational inertia, and that'd be 3 kilograms times, it's only 3 meters from the axis squared, so times 3 meters squared. And if we add all this up and plug all this into the calculator, we'll get that the alpha, the angular acceleration, is going to be 1.83 radians per second squared. So that's the rate at which this object would start accelerating. If it started from rest, it would start to speed up in this direction and start speeding up over and over and over if these forces maintained the torque that they were exerting. So recapping, just like Newton's second law relates forces to acceleration, this angular version of Newton's second law relates torques to angular acceleration, and on the bottom of this denominator isn't the mass, it's the rotational inertia that tells you how difficult it's going to be to angularly accelerate an object. And you can find the moment of inertia of a point mass as mr squared, and you could find the moment of inertia of a collection of point masses by adding up all the contributions from each individual mass.